Hi all, Dr. Metter here. Let's talk a little bit about solving problems with energy. And basically when we talk about solving problems with energy, we mean transforming energy from one type to another. In positive physics, they have very specific terms for adding or losing energy from the system. When you add energy to the system, then you're doing work on the system, which we said before. But the difference is that when you lose energy from the system, if there's a loss of energy of the system, instead of saying the energy does work on something else, positive physics calls it a loss of energy. And so this is energy lost. And specifically, this loss is due to heat being lost from the system through a frictional or drag force. So anytime there's a loss of energy, it's loss due to heat through friction or drag. And then of course we can transform energy, okay? And transforming energy is just transferring it from one type to another. And that could be transferred through work being done or through a loss of energy due to friction or drag. So transforming it is just a general term that means energy is transferred from one type to another. So this is energy is transferred between types. Okay, so let's remember what our different types are. We have gravitational potential energy. We have elastic potential energy. Those are our stored energies. We have kinetic energy, which is energy due to motion. And we have our thermal energy, which is our energy due to heat. And that is energy that's lost due to friction or drag. Okay, let's look at an example. Clear this off. Okay, so our example, in this example, we are going to neglect drag and friction. So we're just looking at energy transfer without that loss from heat. Say we have a cart on a hill, and we're going to set our reference point right here. So this is our reference point is equal to 0, where h is equal to 0. And then that tells us that we can have some height that's relative to that reference point. So if this is point A and this is point B, we can see at point B that cart will be moving and it'll be at our reference point of 0. So at this point right here, we're some height above our reference 0, and therefore our gravitational potential energy or our stored energy is going to be something. We don't know what it is right now, but it's not going to be 0. But if we look at our kinetic energy, well, our kinetic energy, there's no movement right now. So therefore, our kinetic energy is going to be equal to 0. Now, when we get down to point B down here, we do have motion of our cart. So our kinetic energy will be something, right? It will not be equal to 0. But now we've reached a height of 0 because we're at our reference point of 0. So our gravitational potential energy will equal 0. Because we've neglected drag and friction, we know that there's no thermal energy involved or loss of energy due to the heat here. And because we're not dealing with a spring, we have no elastic potential energy. So all of that energy that was stored in our cart for gravitational potential energy has now been converted to the only thing it can be converted to, which is kinetic energy. So our gravitational potential energy at point A is equal to our kinetic energy at point B. All of that stored energy has been converted into the energy of motion once it reaches the bottom of that hill. All right, so let's look at another example. I'm just going to erase some of this. Okay, so now let's not neglect drag. So now there is some type of drag or friction. So let's see, take this out here. Okay, so now if that's the case, I'm gonna take this up here, then what happens at the bottom? Well, we still have some of that potential energy converted to kinetic energy. So this will be non-zero, not equal to zero, and this still will be zero at the bottom, our gravitational potential energy. But while this cart is moving down, we have some loss of thermal energy due to friction, right? Because this is like a bumpy road and there's some friction there. So now once this cart gets to the bottom, it's not, the gravitational potential energy is not going to be equal to the kinetic energy anymore, because some of that energy has been lost. So the gravitational potential energy that it started with will actually be greater than the kinetic energy of the object at the bottom, because some of that energy was lost to thermal energy. So if we wanted to mathematically describe this, we can say, okay, well, this is the gravitational potential energy at point A, which is the most energy it could have, because that's all that's stored, minus the thermal energy that's lost due to friction or drag, is then equal to the kinetic energy that it experiences at the bottom of the hill. Okay, so this would be our equation for this scenario where we are not neglecting drag or friction. Okay, so let's look at another scenario. Now I'm going to clear it. Okay, so let's look at another scenario. So in this one, we neglect drag and friction. Okay, so there'll be no thermal energy, but we do have a motor that that propels the cart down. Okay, so we have our hill, we have our reference 0 point, we have our cart that's some height h above on the hill. And now, and of course this is point A, this is our cart at point B. Here again, we have a potential energy stored, which is equal to something, right? It's non-zero. And our kinetic energy is equal to 0 here because it's not moving. As it goes down, there is work being done on the system by the motor, or on the cart. So the work being done on the cart, which which adds energy to the cart, right? Because work being done on the system, on the cart, adds energy to the cart. So now if we think about the relative values of our potential energy that's been stored at point A and our kinetic energy at point B, then we know that our kinetic energy at point B is going to be greater than our gravitational potential energy that's been stored, because as we went down, that motor was adding energy to the system. So now if we want to mathematically describe this, we can say our gravitational potential energy at point A plus the work done on the system by the motor is equal to the kinetic energy at point B, okay, where that kinetic energy is greater than our initial gravitational potential energy. So what if we say that both, so that's this, what if we say that we do not neglect, let's just say we haven't neglected drag and we have a motor, okay? So in that sense, we're going to have, this situation card here. Okay, so now when we go on, we have work being done, but we also have friction, which is being lost to, thermal energy. And then we get down here, it's moving. So how would we describe that mathematically? Well, we know we start with our gravitational potential energy at point A. We know that there's work being done by the motor, so we add that in because that's energy added to the system. And then we know that there's friction because this is a bumpy road. So there's energy being lost to heat or thermal energy. So that's taking away from the system. So that is, we subtract our thermal energy. This will then give us what our kinetic energy is at the very end. Okay, so in this scenario where we do not neglect drag or friction, and we have a motor, then we have this mathematical equation to describe our system. Okay, again, we're talking about transferring energy, transforming energy from one type to another. That's what all of these problems deal with. All right. Okay, so that is, we're going to stop there for this video. And in the next video, we'll talk about how do we specifically calculate each type of energy that we've been dealing with here in general terms. Good work. Okay, talk to you soon. Bye.